Tonight, we're going to journey to the very edge of time itself. Not the future, the past. Because there is a moment in the history of the universe, a specific instant, beyond which we can never see. No telescope will ever show us what came before it. No technology, no matter how advanced, will ever pierce through it. It is not a question of building better instruments or waiting long enough. It is a fundamental wall built into the fabric of reality itself. And here is what makes it truly extraordinary. This moment happened 13.8 billion years ago, and its faint afterglow is still surrounding us right now, filling every cubic inch of space, passing through your body as you listen to these words. It is the oldest thing we will ever observe, and understanding why changes everything. Before we dive in, if you find these kinds of deep explorations fascinating, a quick like or subscribe would really help this channel grow. It is a small gesture on your part, but it makes a genuine difference for me. Now, let's begin. Let us start with something you already know, but probably have not thought deeply about. When you look at anything at all, you are seeing the past. Not the present, the past. This is true for everything you have ever looked at in your entire life. It is true right now as you read these words, or listen to this voice. It is true for the face of someone sitting across the table from you. It is true for the screen in front of you. It is true for the walls of the room you are in. Nothing you have ever seen has been in the present. Everything has been the past. The reason is simple. Light has a speed. It is an extraordinarily fast speed, roughly 300,000 kilometers per second, but it is a speed nonetheless. It is not infinite. Light takes time to travel from one place to another. When light bounces off an object and enters your eye, there is a delay between when the light left that object and when it arrived at your retina. In everyday life, this delay is so incredibly short that it might as well be zero. Light crosses a typical room in about 10 billionths of a second. Your brain cannot perceive a delay that short. So, as far as your conscious experience is concerned, you are seeing the present. But technically, physically, you are not. You are seeing the past. It is just a past so recent that it makes no difference. But what happens when the distances grow? What happens when the light has to travel not across a room, but across the vacuum of space? That is when this simple fact, light takes time to travel, becomes one of the most powerful ideas in all of science. Let us build up slowly, starting with what is familiar. The moon, our nearest celestial neighbor. The moon orbits Earth at an average distance of about 384,000 kilometers. Light traveling at 300,000 kilometers per second covers that distance in about 1.3 seconds. That means when you look at the moon on a clear night, you are not seeing the moon as it is right now. You are seeing the moon as it was 1.3 seconds ago. If something happened on the lunar surface at this exact moment, if a meteorite struck and threw up a plume of dust, you would not see it for just over 1 second. The event would happen, and then you would wait, and then the light carrying the news of that event would finally reach your eyes. During the Apollo missions, this delay was noticeable. When astronauts on the moon spoke to mission control in Houston, their words traveled as radio signals at the speed of light. Each word took about 1.3 seconds to reach Earth. When Mission Control replied, their response took another 1.3 seconds to reach the Moon. The result was a roughly 3-second gap in every exchange. If you listen to the original recordings, you can hear it. That characteristic pause, that lag. It was not a technical glitch. It was the speed of light imposing its rules on human conversation across 384,000 kilometers of empty space. Now let us go further. The Sun. The Sun is about 150 million kilometers from Earth. Light from the Sun takes approximately 8 minutes and 20 seconds to reach us. So when you see the Sun in the sky, you are not seeing it as it is. You are seeing the Sun as it was over 8 minutes ago. If the Sun suddenly changed color or dimmed or even vanished, you would not know for over 8 minutes. You would keep seeing the Sun shining normally because the photons carrying the information about the change would still be in transit, still crossing the gulf between the Sun and the Earth. For 8 minutes and 20 seconds, you would be watching a star that no longer looked the way you think it does. You would be watching a memory written in light. This has practical consequences that go beyond philosophical curiosity. When NASA operates spacecraft near the Sun, every command sent from Earth takes minutes to arrive. If the Parker Solar Probe encounters an anomaly during its closest approach to the Sun, ground controllers on Earth will not know about it for several minutes. Their corrective commands will take additional minutes to arrive. The spacecraft must handle emergencies on its own because the speed of light creates an unavoidable communication gap. Mars is even worse. Depending on where Mars and Earth are in their respective orbits, the distance between them varies from about 55 million kilometers at the closest to about 400 million kilometers at the farthest. That translates to a light travel time of anywhere from roughly 3 minutes to over 22 minutes one way. When Perseverance sends a photograph from the Martian surface, that photograph was taken minutes before it appears on a screen at the Jet Propulsion Laboratory. The rover cannot be driven in real time like a remote-controlled car. Instead, engineers study images from the previous day, carefully plan a route, write detailed sequences of commands, transmit those commands across millions of kilometers, and then wait. If something goes wrong, if the rover encounters an unexpected rock or a patch of treacherous sand, they cannot react instantly. The delay means every problem takes far longer to solve than it would if the rover were sitting in a parking lot on Earth. Saturn sits roughly 1.2 billion kilometers away at its closest approach to Earth. Light takes over an hour to cross that distance. When the Cassini spacecraft orbited Saturn between 2004 and 2017, every image it sent home was already over an hour old by the time it reached Earth. Engineers could not guide the spacecraft in real time. They programmed entire sequences of maneuvers days or weeks in advance and uploaded them to Cassini. If the spacecraft encountered trouble, it had to be smart enough to recognize the problem and enter a safe mode on its own. Because by the time the problem was communicated back to Earth and new commands were sent in response, over 2 hours would have elapsed. These are sobering delays. Hours. Tens of minutes. But they are small compared to what comes next. Because when we leave the solar system and start talking about the distances to other stars, the delays stop being measured in minutes or hours and start being measured in years. The nearest star to our Sun is Proxima Centauri. part of the Alpha Centauri triple star system. It is about 4.24 light years away. A light year, despite having the word year in it, is not a unit of time. It is a unit of distance. It is the distance light travels in 1 year, roughly 9.46 trillion kilometers. When you look at Proxima Centauri, assuming you could see it because it is a dim red dwarf invisible to the naked eye, you would be seeing light that left that star more than 4 years ago. If Proxima Centauri exploded tonight in some cataclysmic event, you would not know for over 4 years. You would keep seeing a perfectly normal star, a ghost image of something that no longer exists, because the light carrying the news of its destruction would still be crossing the interstellar void. Sirius, the brightest star in the night sky, sits about 8.6 light years away. The light reaching your eye from Sirius tonight departed that star roughly 8.5 years ago. If you are 30 years old, you are seeing Sirius as it was when you were about 21. The star you see is not the star as it is. It is the star as it was, frozen in a moment from your past. Vega, another bright star, is around 25 light years distant. Its light started traveling toward Earth around the year 2000. Think about what has happened on Earth since those photons began their journey. Entire technological revolutions, political upheavals, billions of human lives lived and ended. And those photons were already in flight before any of it happened, silently crossing the emptiness between Vega and Earth, oblivious to everything that occurred on our small world during their 25-year voyage. Now, consider Betelgeuse, the famous red supergiant marking the shoulder of the constellation Orion. Betelgeuse is roughly 650 light years away. The light you see from Betelgeuse tonight left that star around the year 1375, during the Middle Ages. In the early stirrings of the Renaissance, before Columbus, before the printing press, when that light began its journey, most Europeans had never seen a printed book. The Byzantine Empire still existed. The Black Death had only recently swept across the continent, and for 700 years, those photons traveled through the darkness of interstellar space, crossing an almost incomprehensible distance to arrive at your retina tonight. Here is the unsettling part. Betelgeuse is a massive star nearing the end of its life. It will eventually explode as a supernova, an event so energetic it will briefly outshine entire galaxies. Astronomers estimate this could happen any time within the next 100,000 years or so. But because Betelgeuse is 700 light years away, it could have already exploded. The explosion might have happened 300 years ago, or 500 years ago, or last Tuesday. We would have absolutely no way of knowing. The light from that explosion would still be traveling toward us, still crossing the void. We would continue to see Betelgeuse shining calmly in Orion for centuries after it had been destroyed. We will be watching a star that no longer exists, entirely unaware of its fate. This is one of the most profound realizations in all of science. When you look at the night sky, you're not seeing the universe as it is. You're seeing a mosaic of the past. Every point of light comes from a different moment in history. The moon as it was 1 second ago, the sun as it was 8 minutes ago, Proxima Centauri as it was 4 years ago, Betelgeuse as it was 7 centuries ago. The night sky is not a snapshot of the present. It is a collage assembled from light that left its sources at wildly different times. Each star, each point of light, is a time capsule, carrying information about a moment that has already passed. And the farther you look, the further back in time you see. This is the key insight. Distance equals time when you're looking through a telescope. Every telescope is a time machine. Let us keep going. Because stars, even distant ones like Betelgeuse, are relatively close by cosmic standards. The real depths of time open up when we look at galaxies. Our galaxy, the Milky Way, is about 100,000 light years across. Stars on the far side of the galaxy sent their light 100,000 years ago. But the Milky Way is just one galaxy among trillions. The nearest large galaxy, Andromeda, lies about 2.5 million light years away. When you look at Andromeda, and you can see it with the naked eye on a dark, clear night as a faint smudge in the constellation of the same name, you are seeing light that left that galaxy 2.5 million years ago. Our earliest ancestors in the genus Homo were just beginning to emerge, and crude stone tools were first being used. Modern humans did not exist. The genus Homo had barely emerged. That is how far back in time you're looking when you observe Andromeda. 2.5 million years of travel through the intergalactic void. And those ancient photons arrive at your eye tonight, carrying an image of a galaxy as it was before humanity existed. Galaxies in the Virgo cluster are roughly 54 million light years away. When you observe them through a telescope, you're seeing them as they were 54 million years ago, roughly 12 million years after the asteroid impact that wiped out the non-avian dinosaurs. Mammals were diversifying across the planet. Early primates were beginning to evolve. The world was still recovering from one of the greatest mass extinctions in history. And the light from those galaxies, the light that is only now reaching our telescopes, was already on its way. The Hubble Space Telescope and the James Webb Space Telescope have pushed these boundaries even further. They have observed galaxies billions of light years away. Some of the most distant galaxies detected by James Webb are so remote that their light has been traveling for over 13 billion years. These galaxies appear as they were when the universe was less than 1 billion years old. They are small, chaotic, irregular clumps of young stars. They look nothing like the grand spirals and majestic ellipticals we observe in the nearby universe, because they have not had time to evolve. They are cosmic infants, captured in light that has been crossing the expanding universe for nearly its entire history. This is where the concept of looking back in time becomes genuinely powerful. By observing objects at different distances, astronomers can literally watch the universe age. Nearby galaxies reveal the universe as it has been in relatively recent times. Galaxies 1 billion light years away show us the universe 1 billion years ago. Galaxies 10 billion light years away show us the universe 10 billion years ago. Astronomers can trace how galaxies formed and merged, how stars were born and died, how the chemical composition of the cosmos changed over billions of years, all by pointing telescopes at different distances and therefore different epochs. But there must be a limit. There must be a boundary beyond which we cannot see. The universe is 13.8 billion years old. Light has had only 13.8 billion years to travel toward us. Beyond a certain distance, The light simply has not arrived yet. It is still in transit, still crossing space, and it will not reach us for millions or billions of years more. This boundary defines what astronomers call the observable universe, the sphere around us within which light has had time to reach us since the Big Bang. You might expect the observable universe to be 13.8 billion light years in radius. After all, the universe is 13.8 billion years old, and light travels 1 light year per year. But the actual radius of the observable universe is much larger, about 46.5 billion light years. The diameter is roughly 93 billion light years. How can this be? How can we see objects that are 46 billion light years away in a universe that is only 13.8 billion years old? The answer is expansion. The universe has been expanding since the Big Bang. Space itself has been stretching. When a galaxy emitted the light we are now receiving, that galaxy was much closer to us. But during the billions of years that the light was traveling toward us, the space between us and that galaxy was expanding, carrying the galaxy farther away. By the time the light finally arrives, the galaxy has been swept to a much greater distance than where it was when it emitted the light. The light we see is old, but the source that emitted it is now far away. This expansion of space was first discovered by Edwin Hubble in 1929. Hubble observed that distant galaxies are moving away from us, not because they're flying through space under their own power, but because space itself is stretching, carrying the galaxies along with it. The farther away a galaxy is, the faster it recedes. This relationship, known as Hubble's law, was one of the most important discoveries in the history of astronomy. It showed that the universe is not static. It is dynamic, evolving, expanding. The expansion also has a dramatic effect on the light traveling through it. As space stretches, the light waves traveling through that space get stretched too. This stretching shifts the light toward longer wavelengths, toward the red end of the electromagnetic spectrum. This phenomenon is called redshift. A galaxy that emitted blue light billions of years ago will have that light redshifted by the time it reaches us. The more distant the galaxy, the more the light has been stretched, and the greater the redshift. For the most distant objects in the observable universe, the redshift is enormous. Light that was emitted as visible light, the kind your eyes can detect, has been stretched so dramatically that it becomes infrared radiation or even microwave radiation by the time it arrives at Earth. This is precisely why the James Webb Space Telescope was designed to observe primarily in infrared. The most ancient, most distant light in the universe has been stretched far beyond what human eyes or visible light telescopes can detect. You need an infrared telescope to see the earliest galaxies because their light has been traveling through expanding space for so long that it has been shifted completely out of the visible spectrum. So here we are. We have the telescopes that can peer billions of light years into space and therefore billions of years into the past. We can see galaxies as they were when the universe was young. We can trace the evolution of cosmic structure across almost the entire history of the universe. But there must be an oldest thing we can see, a furthest moment we can reach, a boundary beyond which no light exists for us to collect. What is that boundary? What is the absolute oldest observation we can ever make? The answer is not a galaxy. It is not a star. It is not a quasar or a nebula or any familiar astronomical object. It is something far more ancient and far more strange. It is a faint, nearly uniform glow of microwave radiation that fills the entire sky, coming from every direction, with the temperature of about 2.725 degrees above absolute zero. It is called the cosmic microwave background, and it is the afterglow of the Big Bang itself. This radiation was released approximately 380,000 years after the Big Bang. That might sound like a long time, and by human standards it is. But the universe is 13.8 billion years old. 380,000 years is a tiny fraction of that. It represents about 0.003% of cosmic history. When you observe the cosmic microwave background, you're looking back through 99.997% of the universe's entire existence. You are seeing almost all the way back to the beginning. Almost, but not quite. And that tiny gap, that fraction of a percent you cannot see with light, hides some of the most important events in the history of everything. The formation of the first atomic nuclei, the creation of matter as we know it, the emergence of the fundamental forces of nature, perhaps even the origin of space and time themselves. But why does this wall exist? Why can we see no further back than 380,000 years using light? The answer has nothing to do with the power of our telescopes or the sensitivity of our instruments. It is physical. It is built into the nature of the universe itself. Before that moment, the universe was opaque. Light could not travel freely. It was trapped in a blazing fog that filled all of space. And understanding why it was trapped, how it was finally released, and what that ancient glow tells us about the birth of the cosmos is one of the most extraordinary stories in all of human science. To understand the oldest light in the universe, you first need to understand what the universe was like before that light existed. And the truth is, the early universe was nothing like what you see when you look up at the sky today. There were no stars, no galaxies, no planets, no atoms, nothing you would recognize as matter in any familiar sense. The universe in its infancy was a place so extreme, so alien to everything in your experience, that describing it requires you to abandon almost every assumption you have about the way things work. 13.8 billion years ago, the universe began in an event we call the Big Bang. The name is somewhat misleading. Most people hear the words Big Bang and picture an explosion. Something blowing up and sending debris flying outward into empty space. But that is not what happened. There was no empty space for anything to fly into. There was no outside. The Big Bang was not an explosion in space, it was an expansion of space. All of space, all of energy, all of matter, everything that exists, was compressed into an unimaginably hot, dense state. And then space itself began to stretch. Not into anything. It just stretched, it expanded. And as it expanded, the universe cooled. In the very first moments, conditions were beyond anything that exists anywhere in the universe today. The temperature was trillions upon trillions of degrees. At these temperatures, matter as you know it could not exist. There were no atoms, no molecules, no solid objects of any kind. Instead, the universe was filled with a seething, furious soup of fundamental particles. Quarks, the building blocks of protons and neutrons. Electrons. Photons, which are particles of light. Neutrinos, and other subatomic particles, all crammed into an incredibly dense, incredibly hot plasma. Photons existed in enormous numbers. Light was everywhere. But here is the critical thing. That light could not travel. Not in any meaningful sense. In a plasma this dense and this hot, photons could not move more than a tiny distance before slamming into a free electron and being scattered in a random direction. Imagine trying to walk through a crowd so dense that every time you take a step, someone bumps into you and sends you stumbling in a completely different direction. You would never get anywhere. You would just bounce around endlessly, never making progress. That is what photons were doing in the early universe. They were emitted, scattered, absorbed, re-emitted, scattered again, over and over and over, countless times per second. They were trapped. The universe was full of light, but that light was going nowhere. The universe was opaque, blindingly bright, unimaginably hot but completely impenetrable, like being inside a furnace where the glowing walls extend in every direction forever. As the universe expanded, it cooled. This cooling happened gradually but relentlessly. Over the first 20 minutes or so, conditions changed dramatically. The temperature dropped from trillions of degrees to about 1 billion, and then kept falling. During a brief window in those first minutes, nuclear reactions forged the nuclei of the lightest elements, mostly hydrogen and helium, from the raw protons and neutrons that filled the cosmos. We will explore this process in detail later, because it is one of the most precisely understood events in all of cosmology, and provides extraordinary evidence for what happened in those hidden first minutes. But the important point for now is what did not change. Even after these nuclei formed, the fundamental situation remained the same. Bare atomic nuclei, mostly hydrogen and helium, floated in the plasma, but free electrons still filled the space around them. These electrons were too energetic, moving too fast, to be captured by the nuclei. Every time an electron came close to a nucleus, it had too much kinetic energy to be held. It would fly right past or bounce off. Without electrons settling into orbits around nuclei, no atoms could form. And without atoms forming, the plasma persisted. Photons continued to scatter off free electrons. The universe remained opaque. Light remained trapped. This situation persisted for a staggeringly long time. Not long by the standards of the universe today, but long by the standards of the early universe where everything happened quickly. For 380,000 years, the cosmos was a glowing fog, a hot plasma filling all of space. Light bouncing endlessly between charged particles, unable to travel any significant distance. If you were somehow present during this era, which is of course impossible since you are made of atoms and atoms did not yet exist, you would see nothing. Not darkness, the opposite. Blinding, featureless light in every direction, no structure, no detail. Just a uniform blazing glow extending to infinity. You could not see through it any more than you can see through a solid wall. And then, at roughly 380,000 years after the Big Bang, the universe crossed a threshold. The temperature dropped to about 3,000 degrees Kelvin. This is roughly half the temperature of the surface of the sun. Still incredibly hot by human standards, but cool enough for something extraordinary to happen. At this temperature, free electrons finally slowed down enough to be captured by atomic nuclei. Hydrogen nuclei grabbed electrons and became neutral hydrogen atoms. Helium nuclei grabbed electrons and became neutral helium atoms. For the first time in the history of the universe, complete atoms existed. This event is called recombination. The name is technically a misnomer because the electrons and nuclei had never been combined before, so they were not recombining. They were combining for the first time. But the name stuck, and astronomers have used it ever since. Recombination did not happen all at once. It was a gradual process, unfolding over roughly 100,000 years. As the universe cooled, more and more electrons were captured, and the plasma slowly transitioned from fully ionized to mostly neutral. But the key transition, the point where enough atoms had formed to make the universe effectively transparent, happened around 380,000 years. And when it happened, everything changed. Neutral atoms behave completely differently from free electrons when it comes to interacting with light. A free electron is an extremely effective scatterer of photons. Photons bounce off free electrons readily and frequently. But a neutral atom, at the energy levels present at 3000 degrees Kelvin, is largely transparent to photons. Photons pass right through neutral atoms without being scattered. When the electrons combined with nuclei, the scatterers vanished. The fog cleared. Suddenly, light could travel freely through the universe for the first time. This moment is called the surface of last scattering. It is the last moment when photons interacted significantly with matter. After this, photons streamed freely through space, traveling in straight lines, no longer bouncing between electrons. Those photons were released in every direction from every point in the universe. They carried with them a snapshot of what the universe looked like at that instant. The temperature of the plasma, the density variations, the distribution of matter and energy. All of this information was encoded in those photons and preserved as they traveled through space. And those photons have been traveling ever since, for over 13 billion years, across the vast, expanding cosmos, getting stretched by the expansion of space, cooling as the universe cooled. When they were released, they had a temperature of about 3000 degrees Kelvin. They were visible light, glowing orange-red, like the surface of a cool star. But over 13.8 billion years, the expansion of space has stretched their wavelengths by a factor of roughly 1,100. What was once visible light has been stretched into microwaves. Today, those ancient photons have a temperature of just 2.725 degrees Kelvin. That is 2.725 degrees above absolute zero, the coldest anything can possibly be. These photons are now incredibly faint, incredibly cold microwave radiation. But they are everywhere. They fill the entire sky. They come from every direction. There is no spot in the sky, no matter where you point a detector, where this radiation is absent. It permeates the entire universe. This ancient glow is called the cosmic microwave background, commonly shortened to CMB. It is the oldest light in existence, not just the oldest light we have happened to detect. The oldest light that is physically possible, No electromagnetic radiation from before recombination can reach us, because the universe was opaque before that time. The CMB is the earliest image of the universe that light can provide. The discovery of the cosmic microwave background is one of the greatest stories in the history of science, and it began with an accident. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey. They were using a large horn-shaped antenna that had originally been constructed for satellite communication experiments. The antenna was designed to be extremely sensitive to microwave signals, and Penzias and Wilson wanted to repurpose it for radio astronomy. But as they began their observations, they encountered a problem. No matter where they pointed the antenna, no matter what time of day or night, no matter what season, they detected a persistent low-level noise, a faint, steady hiss of microwave radiation that seemed to come from everywhere in the sky equally. They assumed it was an error, a malfunction in the antenna, interference from nearby New York City, about 60 kilometers away. They checked every component of the system. They tightened connections. They tested electronics. They looked for any possible source of the unwanted signal. They discovered that pigeons had been nesting inside the large horn of the antenna and had left droppings on the interior surfaces. Penzias and Wilson carefully removed the birds, cleaned out the droppings, which they diplomatically referred to in their notes as a white dielectric material, and tested again. The noise was still there, unchanged, constant, coming from every direction in the sky with precisely the same intensity. It did not vary with the time of day, which ruled out a terrestrial source. It did not vary with the season, which ruled out a solar system source. It did not vary with the direction of the antenna, which meant it could not be coming from any single object or region. Whatever was producing this signal was filling the entire sky uniformly. Meanwhile, less than 60 kilometers away at Princeton University, a team of physicists was actively searching for exactly this kind of radiation. Robert Dicke, along with colleagues Jim Peebles, Peter Roll, and David Wilkinson, had independently predicted that if the Big Bang theory was correct, there should be a faint afterglow of microwave radiation filling the universe. The logic was straightforward. If the early universe was hot and dense, it would have been glowing with thermal radiation. As the universe expanded and cooled, that radiation would have cooled too, and by now it should have a temperature of only a few degrees above absolute zero, placing it squarely in the microwave part of the electromagnetic spectrum. The Princeton team was building their own antenna to search for this predicted signal. When Penzias, still puzzled by the mysterious noise, contacted Dicke to discuss it, Dicke immediately understood what they had found. He reportedly turned to his colleagues after the phone call and said something along the lines of, "Boys, we have been scooped." Penzias and Wilson had stumbled upon the cosmic microwave background, the afterglow of the Big Bang, without even knowing what they were looking for. Their discovery was published in 1965 as a companion paper alongside the Princeton team's theoretical explanation. It was one of the most important observations in the history of science. Before this discovery, the Big Bang was just one of several competing models for the origin of the universe. Many prominent scientists favored the steady-state model, championed by Fred Hoyle, Hermann Bondi, and Thomas Gold. The steady-state model proposed that the universe had no beginning. It had always existed in roughly its present form, with new matter continuously created in the voids left by the expanding universe to maintain a constant average density. The steady-state universe was eternal and unchanging on the largest scales. There was no moment of creation, no beginning of time. The universe simply was, and always had been. The discovery of the CMB effectively ended that debate. The steady-state model had no explanation for this uniform microwave glow. If the universe had always existed in its current state, there was no reason for this radiation to exist. But the Big Bang model predicted it. A hot, dense early universe that expanded and cooled would necessarily produce exactly this kind of background radiation at exactly this temperature. The prediction matched the observation. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery. But detecting the CMB was only the first step. The real scientific treasure lay hidden in its details. If the early universe had been perfectly smooth, with matter and energy distributed with perfect uniformity everywhere, then the CMB should be perfectly uniform too. The same temperature in every direction, down to the finest measurement. And to a first approximation, it is spectacularly uniform. The temperature of the CMB is 2.725 Kelvin everywhere in the sky, consistent across billions of light years, consistent to an almost eerie degree. This uniformity is itself powerful evidence for the Big Bang model, which predicts that the early universe was very nearly homogeneous, but not perfectly homogeneous. Cosmologists predicted that there should be tiny, almost imperceptibly small variations in the CMB temperature. Not large differences, not even differences you could measure with ordinary instruments. Differences of about 1 part in 100,000, 100,000th of a degree. Some spots in the sky should be a tiny fraction warmer than average, and other spots should be a tiny fraction cooler. These variations, called anisotropies, would reflect the tiny density differences that existed in the early universe. Regions that were slightly denser than average would appear slightly warmer. Regions that were slightly less dense would appear slightly cooler. These tiny differences matter enormously because they are the seeds of everything. Every galaxy, every star, every planet, every living thing that has ever existed grew from these minuscule density fluctuations. In the early universe, regions that were slightly denser had slightly stronger gravitational pull. They attracted a little more matter from their surroundings. Over millions and billions of years, gravity amplified these small differences. Dense regions grew denser. Less dense regions became emptier. The dense regions eventually collapsed under their own gravity to form the first stars, the first galaxies, the first galaxy clusters. The entire cosmic web of structure that we see today, the filaments of galaxies, the voids, the superclusters, all of it grew from those tiny temperature variations in the CMB. The universe's largest structures had their origins in fluctuations so small they are barely detectable. Finding these fluctuations required instruments of extraordinary sensitivity. The first satellite dedicated to mapping the CMB was the Cosmic Background Explorer, known as COBE, launched by NASA in 1989. COBE carried instruments specifically designed to measure the CMB with unprecedented precision. Its first major result was confirming that the CMB has a nearly perfect blackbody spectrum. A blackbody is a theoretical object that absorbs all radiation falling on it and emits radiation with a characteristic distribution of wavelengths, determined solely by its temperature. The Big Bang model predicted that the CMB should have a perfect blackbody spectrum, and COBE confirmed this with stunning accuracy. The measured spectrum matched the theoretical prediction so precisely that when John Mather, the lead scientist, presented the data at an astronomy conference, the audience gave a standing ovation. It was one of the most beautiful agreements between theory and observation in the history of physics. But COBE's second major result was even more important. After subtracting the uniform background and correcting for the motion of the Earth through space, COBE detected the tiny temperature fluctuations. For the first time, humanity could see the seeds of cosmic structure imprinted on the oldest light in the universe. The variations were exactly as predicted, about 1 part in 100,000. George Smoot, another lead scientist on the COBE team, described the CMB map as seeing the face of God. It was a poetic way of saying that they were looking at the universe at its most primordial, seeing the conditions from which everything else emerged. Smoot and Mather were awarded the Nobel Prize in Physics in 2006 for this work. After COBE came more advanced missions. The Wilkinson Microwave Anisotropy Probe, known as WMAP, was launched in 2001. WMAP mapped the CMB with significantly higher angular resolution to COBE, revealing finer details in the temperature fluctuations. The patterns in this CMB are not random. They have specific statistical properties that depend on the composition and geometry of the universe. By analyzing these patterns, cosmologists could extract precise values for fundamental cosmological parameters. WMAP determined the age of the universe to be 13.77 billion years, with an uncertainty of only about 60 million years. It confirmed that the universe is geometrically flat. It measured the relative proportions of the universe's energy budget: roughly 5% ordinary matter, 24% dark matter, and 71% dark energy. All of this from analyzing the temperature patterns in light that is over 13 billion years old. Then came the Planck satellite, launched by the European Space Agency in 2009. Planck was the most sensitive CMB experiment ever built, measuring temperatures with an accuracy of a few millionths of a degree. Its maps of the CMB are the most detailed images of the early universe that humanity has ever produced. They reveal the intricate patterns of slightly warmer and slightly cooler regions with breathtaking clarity. Every spot in those maps represents a real physical condition at a real place in the universe, 380,000 years after the Big Bang. Every warm patch is a region that was slightly denser. Every cool patch is a region that was slightly less dense, and those density differences eventually grew into everything we see in the cosmos today. But here is the fact that makes the CMB so important for our story. It does not merely represent the oldest light we have happened to find. It represents the oldest light that can possibly exist. It is not a technological limit. It is a physical limit. A boundary imposed by the nature of the universe itself. Before recombination, the universe was opaque. photons could not propagate through the dense plasma. Any light emitted was immediately absorbed and scattered. No photon from that era survived to carry information to us. The surface of last scattering is not like a curtain we might someday pull aside. It is an absolute barrier. The universe was literally not transparent before this time. There is no light from before 380,000 years after the Big Bang, because light could not travel before then. Think of it this way. Imagine you are standing on the shore of a vast ocean, looking out at the horizon. You can see everything between you and the horizon. You can see waves, ships, islands, everything on the surface of the water out to the point where the curvature of the Earth drops the surface below your line of sight. But beyond the horizon, you see nothing. Not because there is nothing there, but because the geometry of the Earth prevents you from seeing it. No matter how powerful your binoculars, no matter how tall a tower you build, there is a limit to how far you can see on a curved surface. The surface of last scattering is like a cosmic horizon. On our side of it, the universe is transparent. We can see everything. Stars, galaxies, quasars, nebulae, everything that emits or reflects light. But on the other side, the universe was opaque. No light from that era exists for us to see. The CMB is the light from the horizon itself, the last light emitted before the fog closed in. It is the glow of the wall. Every electromagnetic telescope we have ever built or ever will build, whether it observes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays or gamma rays, is ultimately limited by this wall. All electromagnetic radiation is light, just at different wavelengths, and all of it was trapped before recombination. No matter how sensitive our instruments become, no matter how cleverly we design our detectors, no electromagnetic telescope will ever see through the surface of last scattering. The wall is permanent, absolute, final. This means that the cosmic microwave background is the oldest image we will ever have of the universe, at least using light. It shows us the cosmos at an age of 380,000 years. Before that, the universe is hidden from our electromagnetic eyes. And that hidden era, short as it was in cosmic terms, contains some of the most violent, most transformative, and most important events that ever occurred. But hidden from light does not mean hidden from everything. The universe has other messengers, particles and waves that are not electromagnetic, that were not trapped by the plasma, that escaped the early universe long before photons did. These messengers come from even earlier epochs, from times when the universe was not thousands of years old, but seconds old, or fractions of a second old. These messengers are faint. They are extraordinarily difficult to detect. Some we have found indirect evidence for, others we are still searching for. But they exist. They carry information from beyond the wall of light. And they represent our only hope of ever observing what happened in the universe's first moments. The cosmic microwave background is the oldest light, but it is not the oldest signal. There are whispers from even earlier times, ghostly traces from the first second of existence, and perhaps from even before that. Neutrinos that stopped interacting with matter when the universe was 1 second old. Gravitational waves that might carry imprints from a tiny fraction of a second after the beginning. These are the messengers from behind the wall, and they are what we are going to explore next. Because the question we started with was not just about the oldest light, it was about the oldest moment we can ever observe. And to answer that question fully, we need to look beyond light, beyond the electromagnetic spectrum entirely, into the universe before transparency, into the first seconds and fractions of seconds of cosmic history, into an era so extreme that the physics we use to describe the universe today begins to falter, and the laws of nature themselves start to blur and merge into something we do not yet fully understand. The wall of the CMB is real. It is permanent. Light will never carry us past it. But the universe, in its generosity, has given us other ways to reach back even further. Ways that are harder, fainter, more elusive, but also more ancient. And the story of those other ways, of the universe before light, is one of the most fascinating chapters in all of modern cosmology. We have reached the wall. The cosmic microwave background, released 380,000 years after the Big Bang, is the oldest light in the universe. No electromagnetic telescope will ever see past it. But the universe did not begin at 380,000 years. It began at time zero, whatever that means. And between time zero and the moment when light was finally set free, an extraordinary amount happened. In fact, many of the most important events in the entire history of the cosmos took place during this hidden era. The fundamental forces of nature separated from one another. The building blocks of all matter were assembled. The lightest elements were forged. The seeds of every galaxy and every star were planted. All of it happened before the oldest light was released. All of it is hidden behind the wall. So the question becomes urgent. If we cannot see this era with light, can we observe it at all? Can we reach behind the curtain and learn anything about the universe's first moments? The answer is yes, but only partially, only indirectly, and only with enormous difficulty. The universe left clues, faint traces of what happened before transparency. Messengers that are not photons, that were not trapped by the plasma, that escaped the early universe long before light did. These messengers are ghostly, elusive, and in some cases still entirely theoretical, but they exist. And they represent humanity's only hope of ever knowing what happened in the very first moments of everything. To understand these messengers, we first need to understand what was happening in the universe during the hidden era. So let us start from the wall and work our way backward, step by step, deeper and deeper into the past, into conditions so extreme that our everyday understanding of physics begins to buckle under the strain. Just before the surface of last scattering, the universe was a plasma, bare atomic nuclei, mostly hydrogen and helium, swimming in a dense sea of free electrons and photons. The temperature was about 3,000 degrees Kelvin, roughly half the surface temperature of the Sun. This plasma filled all of space with remarkable uniformity. It was hot, glowing, and opaque, but it was not featureless. It had structure, subtle, almost imperceptible variations in density. Some regions were a tiny fraction denser than average, others were a tiny fraction less dense. These variations were incredibly small, about 1 part in 100,000, but they were real. And they were not static. They were oscillating. Here is something remarkable that most people do not know. The early universe had sound, actual sound waves rippling through the plasma. Not sound as you experience it, not vibrations in air that your ears could detect, but pressure waves propagating through the hot plasma at speeds approaching the speed of light. These waves were created by the competition between two opposing forces. Gravity was pulling matter toward the denser regions, trying to compress them further. Radiation pressure, the outward push of photons trapped in the plasma, was resisting this compression, pushing matter back out. The result was oscillation. Matter fell inward under gravity, was pushed back out by radiation pressure, fell inward again, was pushed back again, over and over. Like a cosmic bell being rung, with the entire universe as the resonating chamber. These sound waves, called baryon acoustic oscillations, left a permanent imprint on the cosmic microwave background. The patterns of warmer and cooler spots in the CMB are not random. They have a specific statistical structure determined by the properties of these sound waves. By analyzing these patterns with extraordinary precision, cosmologists can extract information about the composition and geometry of the universe. The relative heights of the peaks in the CMB power spectrum tell us the ratio of ordinary matter to dark matter. The positions of the peaks tell us the geometry of space. The overall shape of the spectrum tells us the age of the universe. All of this information was encoded in sound waves that rang through the cosmos hundreds of thousands of years before the first star ever formed. Now let us go further. Back. Much further. After about 70,000 years, the balance shifted. At this point, the universe passed through an important transition. Before this moment, radiation dominated the universe. The energy density of photons was greater than the energy density of all the matter in the cosmos combined. This might seem strange. The idea that light can have more energy than all the atoms and particles in the universe. But in the extreme heat of the early cosmos, it was the case. Photons were so energetic and so numerous that they outweighed everything else. During this radiation-dominated era, the growth of structure was suppressed. Density fluctuations in the matter could not grow efficiently because the intense radiation pressure smoothed them out. Gravity was trying to pull matter together, but radiation was preventing it. After about 70,000 years, the balance shifted. As the universe expanded and cooled, the energy of individual photons decreased because their wavelengths were being stretched by the expansion of space. Eventually, the total energy density of matter surpassed that of radiation. The universe entered the matter-dominated era. Gravity could now pull matter together more efficiently. Density fluctuations began to grow. The seeds of galaxies, planted in the earliest moments and preserved through the radiation era, could finally start to develop. This transition was a quiet event. Nothing dramatic happened at one specific moment, but it was a turning point. Without it, the galaxies and stars and planets that exist today could never have formed. But let us go much further back, past tens of thousands of years, past thousands, past hundreds, all the way back to the first few minutes of the universe. This is where things become truly dramatic. Between roughly 1 second and 20 minutes after the Big Bang, the temperature of the universe dropped from about 10 billion degrees Kelvin to about 1 billion degrees. These temperatures are comparable to the cores of the most massive stars. And during this brief window, conditions were right for something extraordinary. Nuclear fusion on a cosmic scale. Protons and neutrons, which had formed from the cooling quark-gluon plasma in the first microseconds, were now colliding at tremendous energies and sticking together to form atomic nuclei. This process is called Big Bang nucleosynthesis, and it is one of the most precisely understood events in all of cosmology. The primary product was hydrogen, which requires no fusion at all, since a hydrogen nucleus is simply a single proton. About 75% of the ordinary matter in the universe emerged from nucleosynthesis as hydrogen. About 25% became helium-4, a nucleus containing 2 protons and 2 neutrons. Trace amounts of deuterium, which is a hydrogen nucleus with 1 proton and 1 neutron, were also produced. Tiny quantities of helium-3 and lithium-7 rounded out the inventory. And that was it. Nothing heavier. No carbon, no oxygen, no nitrogen, no iron, no silicon. None of the elements that make up rocky planets or living organisms. Those heavier elements would have to wait billions of years for stars to form, and forge them through nuclear fusion in their cores, and scatter them across space in supernova explosions. Big Bang nucleosynthesis lasted only about 15 minutes. After roughly 20 minutes, the universe had expanded and cooled too much for fusion to continue. The window slammed shut. The nuclear furnace of the early universe turned off, never to reignite. What makes this so remarkable is how precisely we can calculate what should have been produced, and how accurately those calculations match what we actually observe. When astronomers measure the abundance of helium and deuterium in the oldest, most chemically pristine gas clouds in the universe, clouds that have remained largely untouched by stellar processing, they find ratios that match the predictions of Big Bang nucleosynthesis to extraordinary precision. 25% helium, the right amount of deuterium, the right traces of lithium. This agreement is one of the strongest pieces of evidence that the Big Bang model correctly describes what happened in the first few minutes of the universe. We cannot see those minutes with light, but the chemical composition of the universe preserves a record of them, written in the relative abundances of the lightest elements. Now let us push even further back, past the first minutes, into the first seconds. This is where we encounter a messenger older than the cosmic microwave background. A signal from an era when the universe was unimaginably young, when it was not thousands of years old or even minutes old, but 1 single second old. This messenger is not light, it is neutrinos. Neutrinos are among the most mysterious and elusive particles in nature. They have almost no mass. They carry no electric charge. They interact with other matter only through the weak nuclear force and gravity, both of which are extraordinarily feeble at the energies we encounter in everyday life. The result is that neutrinos are ghostly. They pass through matter as if it were not there. Right now, roughly 65 billion neutrinos from the sun are passing through every square centimeter of your body every single second. You do not feel them. You cannot detect them without specialized equipment. They pass through the entire Earth without slowing down or interacting with a single atom. A beam of neutrinos could travel through a wall of lead a light year thick, and most of them would emerge from the other side without having hit anything. But in the very early universe, conditions were different. Temperatures were so extreme and densities were so high that even the weak force was strong enough to keep neutrinos in constant interaction with other particles. Neutrinos were just as trapped as photons were, bouncing around in the dense plasma, colliding constantly with electrons, protons, and other particles. They were in thermal equilibrium with everything else. They were part of the hot, dense soup. But neutrinos decoupled earlier than photons, much earlier. About 1 second after the Big Bang, when the temperature was roughly 10 billion degrees Kelvin, the universe had expanded and cooled enough that neutrinos stopped interacting with other particles. The weak force, already feeble by nature, became too weak to maintain contact. Neutrinos effectively disconnected from the rest of the universe. They stopped scattering. They stopped colliding. They streamed freely through space, just as photons would do 380,000 years later when atoms formed and the electromagnetic fog cleared. But neutrinos did it first, by a margin of hundreds of thousands of years. These primordial neutrinos have been traveling through the universe ever since, for over 13 billion years. They have cooled as the universe expanded, just as the CMB photons cooled. Today, they fill all of space with a predicted temperature of about 1.95 degrees Kelvin. Slightly cooler than the CMB because they decoupled earlier and missed the slight heating that occurred when electrons and positrons annihilated shortly after neutrino decoupling. This sea of ancient neutrinos is called the cosmic neutrino background, or CNB. The cosmic neutrino background is older than the cosmic microwave background. It comes from 1 second after the Big Bang, not 380,000 years. If we could detect it directly, it would be the most ancient signal ever captured by human instruments. It would carry information about the universe at an age of 1 second. An age so young that the universe had not yet fused its first helium nucleus. An age when the entire cosmos was smaller, hotter, and denser than anything that exists anywhere in the universe today. But detecting the cosmic neutrino background is one of the greatest experimental challenges in all of physics. These relic neutrinos have unimaginably low energies. They are far colder and far less energetic than even the solar neutrinos that already pass through us, undetected by our bodies. Current neutrino detectors, which are massive underground facilities designed to catch the rare interactions of higher energy neutrinos from the sun and from supernovae, are nowhere near sensitive enough to detect the cosmic neutrino background directly. The energies are simply too low. The interactions are simply too rare. There have been proposals for future experiments. The most promising is called Ptolemy, which stands for Princeton Tritium Observatory for Light, Early Universe. Massive neutrino yield. The concept is elegant but fiendishly difficult. Tritium, a radioactive isotope of hydrogen, naturally undergoes beta decay, emitting an electron and a neutrino. The energy of the emitted electron has a known maximum value. But if a relic neutrino from the cosmic neutrino background is captured by a tritium atom during the decay process, the electron will be emitted with a tiny amount of extra energy. By measuring the electron energies with extraordinary precision and looking for a slight excess just above the expected maximum, scientists could, in principle, detect the presence of cosmic neutrinos. But the energy difference is unbelievably small. Measuring it would require precision beyond anything currently achievable. We do, however, have strong indirect evidence that the cosmic neutrino background exists. Its gravitational effects are imprinted on the CMB itself. The presence of free-streaming neutrinos in the early universe slightly altered how matter clumped together. Neutrinos, because they move at nearly the speed of light, tend to smooth out density fluctuations on small scales. This smoothing effect changes the pattern of temperature fluctuations in the CMB in subtle but measurable ways. When cosmologists analyze the detailed structure of the CMB using data from the Planck satellite, they find that the patterns are consistent with a universe containing exactly 3 species of neutrinos at the predicted temperature. If the cosmic neutrino background did not exist, the CMB would look different. The fact that the CMB looks exactly as predicted is compelling indirect evidence that the relic neutrinos are there, filling all of space, even though we have not yet touched them directly. Now let us go even deeper, before 1 second, into the first fraction of a second after the Big Bang. This is where we encounter the most speculative, but also the most thrilling possibility for observing the very earliest moments of the universe. A messenger that was never trapped by anything, that has been traveling freely since the instant it was created. That carries information from time so early that even neutrinos were still trapped. That messenger is gravitational waves. Gravitational waves are ripples in the fabric of space-time itself. They were predicted by Albert Einstein in 1915 as a consequence of his general theory of relativity. If mass and energy curve space-time, then changes in the distribution of mass and energy should create ripples that propagate outward at the speed of light. For a century, gravitational waves remained theoretical. They were too faint to detect with any existing instrument. Then, in September 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection. The signal came from 2 black holes spiraling into each other and merging roughly 1.3 billion light-years away. The gravitational waves from that event, after traveling for 1.3 billion years, stretched and compressed the 4-kilometer arms of the LIGO detector by a distance smaller than 1/10,000th of the diameter of a proton. The detection was a triumph of engineering and physics and earned the Nobel Prize in 2017. What makes gravitational waves so extraordinary for probing the early universe is that they interact with matter incredibly weakly, far more weakly than even neutrinos. A gravitational wave can pass through the entire planet without being affected. It can pass through the dense plasma of the early universe without being scattered or absorbed. Unlike photons, which were trapped before recombination, and unlike neutrinos, which were trapped before 1 second, gravitational waves were never trapped. They have always traveled freely. If gravitational waves were produced at any time after the Big Bang, no matter how early, they would have propagated through the universe without hindrance, carrying information about the conditions at the time of their creation. And there is very good reason to believe that the very first fraction of a second after the Big Bang produced gravitational waves. This brings us to one of the most important and bold ideas in modern cosmology: cosmic inflation. Inflation is a theory first proposed by physicist Alan Guth in 1980. It addresses several deep puzzles about the universe that the standard Big Bang model on its own cannot explain. The most famous of these is the horizon problem. The cosmic microwave background has almost exactly the same temperature in every direction. Regions of the sky on opposite sides are separated by vast distances. Light has not had enough time to travel between these regions since the Big Bang. So how did they reach the same temperature? In normal physics, two objects reach the same temperature by exchanging energy, by being in contact. But these regions of the sky have never been in contact. They are too far apart. There has not been enough time since the Big Bang for any signal, even one traveling at the speed of light, to connect them, yet they have the same temperature to 1 part in 100,000. This is like walking into two houses on opposite sides of the planet and finding that both thermostats are set to exactly the same temperature down to the 100th of a degree. It demands an explanation. Inflation provides one. According to inflation, in the very first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. Not the gradual expansion the universe has been undergoing ever since, but an incredibly violent, sudden ballooning of space. In a time interval shorter than a trillionth of a trillionth of a trillionth of a second, the universe expanded by a factor of at least 10 to the power of 26. A region smaller than a single atom was inflated to something larger than the entire observable universe today. Before inflation, the regions that would eventually become opposite sides of our sky were close together, close enough to be in thermal contact, close enough to exchange energy and reach the same temperature. Then inflation blew them apart, stretching them to enormous separations in an instant. They have the same temperature because they were once in contact, long before inflation separated them forever. Inflation also explains why the universe appears to be geometrically flat. Before inflation, space could have had any curvature. It could have been positively curved like the surface of a sphere, or negatively curved like the surface of a saddle, but inflation stretched space so violently and so thoroughly that any curvature was smoothed out. Just as inflating a balloon makes a small patch of its surface appear flat, inflation made the entire observable universe appear flat. And measurements confirm this. The universe is flat to within the precision of our best measurements, exactly as inflation predicts. Perhaps most remarkably, inflation explains the tiny density fluctuations that seeded all cosmic structure. During inflation, quantum fluctuations, the inherent randomness built into the fabric of reality at the smallest scales, were stretched to macroscopic and then cosmic sizes. Quantum mechanics tells us that on the smallest scales, energy and matter fluctuate randomly. Particles pop into and out of existence. Fields oscillate unpredictably. These fluctuations are normally confined to the subatomic realm, far too small to affect anything on human or cosmic scales. But during inflation, the expansion of space was so rapid and so violent that these quantum fluctuations were stretched from subatomic scales to astronomical scales. They became the density variations that we see imprinted on the CMB. They became the seeds that grew into galaxies and galaxy clusters and the entire cosmic web. The origin of all large-scale structure in the universe, every galaxy, every star, every planet, traces back to quantum randomness amplified by inflation in the first fraction of a second. And here is the crucial connection to our story. Inflation would have produced gravitational waves. The violent expansion of space during inflation would have generated ripples in space-time, primordial gravitational waves that propagated through the universe from the moment of their creation. These waves would carry information about the energy scale of inflation, about the physics operating during that unimaginably brief epoch, about conditions at a time when the universe was less than a trillionth of a trillionth of a trillionth of a second old. If we could detect these primordial gravitational waves, we would be observing a signal from incomparably earlier than anything else we have ever measured. The CMB comes from 380,000 years. The cosmic neutrino background comes from 1 second. Primordial gravitational waves from inflation would come from approximately 10 to the negative 36 seconds after the Big Bang. That is a decimal point followed by 35 zeros, and then a 1. It is a span of time so absurdly short that no analogy can convey it. There are more. Of these intervals in a single second, then there are seconds in the entire history of the universe. The number is not merely large, it is beyond human comprehension. We have not yet detected primordial gravitational waves. In 2014, an experiment called BICEP-2, operating a telescope at the South Pole, announced that it had found a signature of these waves imprinted on the polarization of the CMB. The announcement was met with enormous excitement. If confirmed, it would have been one of the greatest discoveries in the history of physics. Direct evidence of inflation and the earliest signal ever detected from the cosmos. But subsequent analysis, including data from the Planck satellite, revealed that the signal was likely caused by dust within our own Milky Way galaxy rather than by primordial gravitational waves. The dust grains, aligned by the galaxy's magnetic field, can produce polarization patterns that mimic the gravitational wave signal. The BICEP-2 result was not confirmed, but the search continues with renewed determination. A new generation of experiments is now operating or being built. The BICEP array at the South Pole, the Simons Observatory in Chile, and the planned Lightbird satellite from the Japanese Space Agency are all designed to measure CMB polarization with the sensitivity needed to detect or definitively rule out the primordial gravitational wave signal. These experiments will be able to distinguish between the signal from dust and the signal from inflation with far greater confidence than BICEP-2 could. There is also the long-term possibility of detecting primordial gravitational waves directly, not through their imprint on the CMB, but by measuring the space-time ripples themselves. The Laser Interferometer Space Antenna, known as LISA, is a planned space-based gravitational wave detector scheduled for launch in the mid-2030s. LISA will consist of 3 spacecraft flying in formation, separated by 2.5 million kilometers, forming a triangle in space. Laser beams will bounce between the spacecraft, measuring the distances between them with extraordinary precision. Passing gravitational waves will stretch and compress these distances by tiny amounts, and LISA will detect those changes. LISA is designed to observe gravitational waves at much lower frequencies than ground-based detectors like LIGO, opening a new window on the gravitational wave universe. While LISA itself is not expected to detect the primordial gravitational wave background directly, it will advance the field enormously. Future generations of space-based detectors, perhaps decades or centuries from now, might achieve the sensitivity needed to detect the faint gravitational whisper of inflation. So let us take stock of where we are. We have 3 messengers, each reaching further back in time than the last. Photons, the particles of light, carry us back to 380,000 years after the Big Bang. The cosmic microwave background is the oldest electromagnetic signal, and it represents an absolute wall for any telescope that detects light. Neutrinos carry us back to about 1 second after the Big Bang. The cosmic neutrino background is older than the CMB by a factor of roughly 12 trillion, but it remains undetected directly. We know it is there from its indirect effects on the CMB, but capturing individual relic neutrinos is beyond our current technology. Gravitational waves carry us back potentially to a tiny fraction of a second after the Big Bang. Primordial gravitational waves from inflation would be the oldest signal of any kind that we could ever detect, carrying information from an epoch so ancient that the universe had not yet produced the particles that would eventually become atoms. Each messenger is fainter than the last. Each is harder to detect. Each reaches deeper into the hidden era. And each tells us something different about the conditions that prevailed in those earliest moments. But there is a limit even to these messengers. There is a moment in the history of the universe beyond which no signal of any kind carries meaningful information. A moment so extreme, so alien, so far beyond the reach of our current understanding, that the very laws of physics as we know them cease to apply. This moment is not defined by the opacity of plasma, or the weakness of particle interactions, or the faintness of space-time ripples. It is defined by something more fundamental. It is defined by the breakdown of physics itself. That moment has a name. It is called the Planck epoch, and it represents the absolute boundary of observation, the oldest moment we can ever hope to describe, let alone observe. Beyond it lies a mystery that may not merely be unsolved, but may be fundamentally unsolvable. Not because we lack intelligence or resources, but because the concepts we use to describe reality, space, time, energy, matter, may simply not apply. The Planck epoch is the ultimate wall, and understanding why it exists, what it means, and what it tells us about the limits of human knowledge is the final chapter of our journey to the oldest moment we can ever observe. We have traced the limits of observation backward through cosmic history. Light takes us to 380,000 years after the Big Bang. Neutrinos, at least in principle, take us to 1 second. Gravitational waves might take us to a tiny fraction of a second, deep into the era of inflation. But now we reach something different. Something final. A barrier that is not just technological or practical, but fundamental. A point in time beyond which the very concept of observation may lose its meaning. This barrier is called the Planck epoch. It is defined by the Planck time, which is approximately 5.4 times 10 to the negative 44 seconds. That is a decimal point followed by 43 zeros, and then a 5. An interval of time so impossibly brief that it makes even the inflationary epoch seem leisurely by comparison. There are more Planck times in a single second than there are seconds in the entire history of the universe. The number is not just large, it is incomprehensible. There is no human experience, no analogy, no metaphor that captures how short the Planck time really is. The Planck epoch is the period from the beginning of the universe, whatever that means, to one Planck, time after it. During this era, the universe was unimaginably extreme. The temperature was at the Planck temperature, approximately 1.42 times 10 to the 32 degrees Kelvin. For perspective, the core of the Sun is about 15 million degrees. The temperature at the center of the hottest stars reaches a few billion degrees. The temperature during Big Bang nucleosynthesis was about 10 billion degrees. The temperature during the Planck epoch was 100 billion trillion degrees. These temperatures are so far beyond anything that exists in the universe today that the comparison is meaningless. It is like comparing the height of a sand grain to the diameter of the observable universe. At this temperature and at the corresponding density, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force are believed to have been unified into a single force. In our everyday experience, and in all experiments we have ever conducted, these forces are distinct. They operate differently, have different strengths, and act on different particles. But at the extreme conditions of the Planck epoch, the distinctions disappear. All four forces become aspects of a single underlying interaction, a single superforce governing a universe so hot and so dense that the very notion of separate forces had not yet emerged. Here is the problem. We have a very good understanding of three of the four forces. The electromagnetic force, the strong force, and the weak force are all described by quantum mechanics, specifically by a framework called quantum field theory. This framework has been tested with extraordinary precision. It predicts the outcomes of particle physics experiments with an accuracy of 10 or more decimal places. It is one of the most successful theories in the history of science. Gravity, however, is described by a completely different theory, Einstein's general theory of relativity. General relativity describes gravity not as a force pulling objects together, but as the curvature of space-time caused by mass and energy. It works beautifully for describing planets, stars, galaxies, black holes, and the large-scale evolution of the universe. It predicted gravitational waves a century before LIGO detected them. It has been confirmed by every experiment and observation ever conducted. But general relativity and quantum mechanics are fundamentally incompatible. They are based on different assumptions about the nature of reality. Quantum mechanics treats space-time as a fixed stage on which particles act out their dramas. General relativity treats space-time as a dynamic entity that bends and stretches in response to matter and energy. These two pictures of reality are in direct conflict. When conditions are mild, when gravity is weak and quantum effects are small, you can use one theory or the other without conflict. In everyday life, and even in most astrophysical situations, one theory dominates and the other is negligible. But during the Planck epoch, neither theory dominates. Both gravity and quantum effects are equally important simultaneously. The universe is so small, so dense, and so hot that you need both theories at the same time. And when you try to combine them, when you try to apply quantum mechanics to gravity, the mathematics breaks down. You get nonsensical answers. Infinite quantities that cannot be removed by any known technique. The theories are telling you that they do not apply, that they are the wrong tools for the job. What is needed is a theory of quantum gravity, a single unified framework that encompasses both general relativity and quantum mechanics. Such a theory would describe how space-time behaves at these smallest scales, at the highest energies, at the most extreme conditions. It would tell us what happened during the Planck epoch. It would tell us whether space and time are truly continuous, or whether they have a granular structure at the tiniest scales. And it would tell us what happened at the very beginning of the universe. But we do not have a theory of quantum gravity. Not yet. There are candidates. String theory proposes that fundamental particles are not points, but tiny vibrating strings of energy. Different vibration patterns produce different particles, just as different vibrations of a guitar string produce different notes. String theory requires extra dimensions beyond the 3 spatial dimensions, and one time dimension we experience. Some versions require 10 or 11 dimensions total, with the extra dimensions curled up so small that we cannot detect them. String theory is mathematically beautiful, and has produced deep insights into the nature of gravity and quantum mechanics. But it has not yet made a prediction that can be tested by experiment. The energies required to probe the scales where string theory makes unique predictions are vastly beyond what any particle accelerator can achieve. Loop quantum gravity takes a different approach. Instead of adding strings and extra dimensions, it proposes that space-time itself has a discrete structure at the smallest scales. Space is not infinitely divisible. At the Planck scale, space is woven from tiny loops, forming a fabric with a granular texture. Time does not flow continuously, but advances in tiny discrete steps. In loop quantum gravity, the Big Bang might not have been the beginning of time. Instead, it might have been a big bounce, where a previously contracting universe reached a minimum size, dictated by the granularity of space-time, and then rebounded into expansion. If this is correct, there is a universe before the Big Bang, and information about it might, in some extremely subtle way, have survived the bounce. There are other approaches. Causal dynamical triangulation builds space-time from tiny building blocks and studies what large-scale structures emerge. Asymptotic safety proposes that gravity becomes well-behaved at very high energies. Emergent gravity suggests that gravity might not be a fundamental force at all, but an emergent phenomenon arising from deeper microscopic physics, much as temperature emerges from the collective motion of atoms. Each of these proposals offers a different picture of what space-time looks like at the Planck scale. None has been confirmed by experiment. None makes predictions that we can currently test. This is the wall. Not a wall of opaque plasma, like the surface of last scattering. Not a wall of weakly interacting particles, like the cosmic neutrino background, but a wall of ignorance. A wall built from the limits of our own understanding. We do not know what happened during the Planck epoch because we do not have the physics to describe it. This means that the Planck time represents the absolute limit of what we can ever reconstruct about the early universe, using our current understanding of the laws of nature. Even if we somehow detect primordial gravitational waves from inflation, those waves were generated after the Planck epoch. Even the most exotic signals we might hope to detect carry no information about conditions before the Planck time because we do not know how to interpret such information. We lack the theoretical framework to decode it. It is as if someone handed you a book written in a language that has never been translated and never will be translated, because the language itself operates on principles completely alien to every language you have ever encountered. You can hold the book, you can see that it contains writing, but you cannot read it. Not because you are not clever enough, but because the very concepts the language expresses have no equivalent in any language you know. Could we ever develop a theory of quantum gravity? Possibly. Many physicists are working on it. It is one of the greatest unsolved problems in physics. If someone does develop a working theory of quantum gravity, it might tell us what happened during the Planck epoch. It might reveal whether time itself has a beginning, whether the Big Bang was truly the start of everything, or whether the universe existed in some other form before it. It might tell us whether the Big Bang was a unique event or one of many, whether our universe is the only one or one of infinitely many in a multiverse. But even with the theory of quantum gravity, there may be limits to what we can observe. Theories make predictions, but predictions need to be tested against observations. During the Planck epoch, conditions were so extreme that any signals generated would have been radically transformed by the subsequent evolution of the universe. Extracting meaningful information about the Planck epoch from observations might be like trying to hear a whisper from before a thunderstorm by analyzing the thunder. The signal might be there in principle, but in practice, it is overwhelmed by everything that came after. Some physicists have speculated about what might lie beyond the Planck epoch. One possibility is that time itself began at the Big Bang. That asking what happened before the Big Bang is like asking what is north of the North Pole. The question seems meaningful, but it has no answer because the concept it invokes does not apply. If time began at the Big Bang, there is no before. The Planck epoch is not just the limit of our observation, it is the limit of time. Another possibility is that the Big Bang was not the beginning, but a transition. Some models propose that the universe existed before the Big Bang in a contracting phase. The universe collapsed to an incredibly dense state and then rebounded, expanding again in what we call the Big Bang. This is sometimes called the Big Bounce. In this scenario, the Planck epoch is not the beginning of time, but a bottleneck, a moment of extreme compression through which information from the previous era might have survived, however faintly. Other models propose that our universe emerged from the collapse of matter in a higher dimensional space, that the Big Bang was the formation of a new region of space-time within a larger, possibly infinite multiverse. In these models, the question of what happened before the Big Bang has an answer, but that answer lies in the physics of dimensions and spaces beyond anything we can directly observe. These are fascinating ideas, but they remain speculative. None has been confirmed by observation. None may be confirmable. We are at the boundary between physics and metaphysics, between science and philosophy. We can make educated guesses, but we cannot be certain. Let us now step back and take in the full picture. Where exactly are we in the story of the universe? What can we actually see when we look back in time, and what remains forever hidden? The universe is 13.8 billion years old. Using light, we can see back to 380,000 years after the Big Bang. That means we can directly observe 99.997% of cosmic history. That is extraordinary. Imagine if you could remember 99.997% of your life, every moment except the very first day. You would have an incredibly complete record. The fraction we are missing is tiny, but it contains some of the most important events that ever happened. Using neutrinos, at least in principle, we can push back to about 1 second after the Big Bang. Using gravitational waves, we might push back to a tiny fraction of a second, into the inflationary epoch. Using the predictions of nuclear physics, we can reconstruct what happened during the first 20 minutes with high confidence. We know the composition of matter that emerged from Big Bang nucleosynthesis. We know the temperature and density of the universe at various times during the first few 100,000 years. But before about 1 trillionth of a second after the Big Bang, our knowledge becomes much less certain. The physics of that era, the electroweak epoch, the quark epoch, the grand unification epoch, is progressively less well understood. We have theories, but they have not been tested at these energies. The most powerful particle accelerator on Earth, the Large Hadron Collider at CERN, can recreate conditions similar to those about 1 trillionth of a second after the Big Bang. It cannot reach the energies of the Planck epoch, which are roughly 1 quadrillion times higher than the Large Hadron Collider can achieve. To reach Planck energies with a particle accelerator, you would need a machine the size of a galaxy. We will never build such a machine. This is not a statement about the limits of human ambition. It is a statement about physical constraints that cannot be overcome. This is why the Planck epoch remains hidden. Not because we are not smart enough to figure it out, though we might not be. Not because we lack the will or the funding, though we sometimes do. But because the universe has placed a fundamental barrier between us and the very beginning. The laws of physics, as we understand them, break down. The signals from that era, if they exist, are buried beneath billions of years of subsequent evolution. And the energies required to recreate those conditions are beyond anything we can achieve or even imagine achieving. And yet, we know an extraordinary amount. Think about what humanity has accomplished. We are a species that evolved on the surface of a small rocky planet, designed by evolution to find food, avoid predators, and reproduce. Our brains evolved to navigate savannas and understand the behavior of medium-sized objects moving at moderate speeds. Nothing in our evolutionary history prepared us for the Big Bang, for quantum mechanics, for the curvature of space-time, for the cosmic microwave background. And yet, we figured it out. Using nothing but our ability to think, to observe, to reason, we reconstructed the history of the universe all the way back to a fraction of a second after its birth. We detected the afterglow of the Big Bang. We measured its temperature to 6 decimal places. We mapped the tiny fluctuations that seeded all the structure in the cosmos. We calculated the abundances of the lightest elements and confirmed them against observation. We predicted the existence of the cosmic neutrino background and found indirect evidence for it. We proposed inflation and are now searching for its gravitational wave signature. We built detectors sensitive enough to measure changes in the length of a 4-kilometer tunnel smaller than 1/10,000th of the diameter of a proton. From a small planet orbiting an ordinary star in a mid-sized galaxy, we reached back 13.8 billion years and touched the edge of time. That is remarkable. That is worth pausing over. No other species on Earth has done this. As far as we know, no other species in the universe has done this, though we cannot be certain. We are matter that has become conscious, atoms that have learned to contemplate their own origins. We are the universe looking back at itself, trying to understand how it began. And the oldest moment we can ever observe, the cosmic microwave background, is not just a scientific curiosity. It is a message from the beginning. It surrounds us at every moment. Right now, as you listen to these words, ancient photons from the surface of last scattering are passing through you. They've been traveling for over 13 billion years, crossing the vastness of expanding space, cooling from a glowing orange to a faint microwave whisper. And they carry information about a moment when the universe was only 380,000 years old. Every cubic centimeter of the room you're in right now contains roughly 400 of these ancient photons. They are everywhere. They outnumber the atoms in the universe by a factor of about 1 billion to 1. You are bathed in the oldest light in existence, and you have been your entire life, even if you never knew it until now. Those photons are the oldest light. They were released at the moment the universe became transparent, the moment atoms formed for the first time. Before that, the universe was a hot, opaque fog. After that, the universe was transparent, and light could travel freely. The boundary between these two eras is the boundary of our vision. The oldest moment we can ever see with light. There is something poetic about this. The universe spent its first 380,000 years in darkness, at least from our perspective. Not darkness because there was no light. There was plenty of light. But darkness because the light was trapped, unable to escape the fog. Then, in a relatively brief period, the fog cleared. Atoms formed. The universe became transparent, and the light was released. It was the cosmic equivalent of opening your eyes for the first time. Before that moment, the universe could not see itself. After that moment, it could. We see that moment now, 13.8 billion years later, as the faint microwave glow of the CMB. It is the first dawn of the universe, the moment when the cosmos first became visible to itself. And everything we see between that first dawn and the present, every galaxy, every star, every planet, every supernova, every quasar, all of it is the universe evolving in the light. The universe spent most of its history transparent and full of structure. But it began in a fog. What lies behind the fog, we can only partially know. Neutrinos tell us about 1 second in. Gravitational waves might tell us about a trillionth of a trillionth of a trillionth of a second in. Nuclear physics tells us about the first 20 minutes, but the very beginning, the Planck epoch, remains beyond our reach. The oldest moment we can ever observe is defined by these boundaries. The CMB for light, the cosmic neutrino background for neutrinos, primordial gravitational waves for space-time ripples, the Planck epoch for all physics. Each boundary takes us closer to the beginning, but none takes us all the way there. They're like nested horizons, each one revealing a deeper layer of the past, each one more difficult to reach than the last. And behind the final horizon lies the ultimate mystery. the origin of everything. And there is a deep lesson in this. The universe has given us extraordinary access to its history. We can see almost everything. We can reconstruct the story of the cosmos with stunning detail and precision. But the universe has also kept something from us. The very beginning. The first instant. The moment of creation, if that is even the right word. That moment remains hidden, possibly forever. Perhaps future generations will develop a theory of quantum gravity. Perhaps they will find ways to extract information from the Planck epoch that we cannot currently imagine. Perhaps they will discover that the Big Bang was not the beginning, but a transition, and that there is a deeper history waiting to be uncovered. Or perhaps the Planck epoch will remain forever beyond our grasp, a permanent boundary at the edge of knowledge. Either way, what we have already achieved is extraordinary. We have looked back 13.8 billion years. We have detected the afterglow of the Big Bang. We have mapped the seeds of all cosmic structure. We have reconstructed the history of the universe to within a fraction of a second of its birth. We have done this from a small world orbiting an ordinary star, using nothing but our curiosity and our intelligence. The oldest moment we can ever observe is the cosmic microwave background. The light released 380,000 years after the Big Bang. It fills the entire sky. It has a temperature of 2.725 degrees Kelvin. It carries the imprint of the earlier structures that will become galaxies, stars, and planets. It is the farthest and oldest thing we will ever see with light. But it is more than a scientific measurement. It is a connection, a bridge between us and the beginning of everything. When you think about the CMB, you are thinking about light that has been traveling since before there were stars, before there were galaxies, before there were atoms, for most of its journey. That light has crossed the entire observable universe to reach you, and it carries a message from the dawn of time. The universe began in a hot, dense state. It expanded and cooled. At 380,000 years, atoms formed and light was released. That light is still here. It is all around you. Right now. You are surrounded by the oldest observable moment in the history of everything. It is not hidden in a distant galaxy. It is not locked away in a laboratory. It is here, everywhere, in every direction, filling every cubic centimeter of the space you occupy. The oldest light in the universe is touching you as you listen to these words. And beyond that light, hidden by the opacity of the early plasma, lies an even older universe. A universe of neutrinos and gravitational waves, and nuclear reactions and quantum fluctuations, and possibly the birth of space-time itself. We can infer some of it, we can calculate some of it, we may one day detect some of it directly, but we may never see the very beginning. And perhaps that is fitting. Perhaps it is right that the universe keeps some secrets, that the very first moment of existence remains just out of reach. It gives us something to strive toward, something to wonder about. A mystery at the edge of everything that reminds us that no matter how much we learn, there is always more. The oldest moment we can ever observe is ancient beyond comprehension, but it is not the beginning. It is close, unimaginably close, but not quite. And that tiny gap between what we can see and what we cannot may be the most tantalizing mystery in all of science. a sliver of hidden time at the start of everything, where the answers to the deepest questions may lie forever just beyond our grasp. Tonight, when you look up at the sky, remember that the oldest light in the universe is there. Not coming from any star or galaxy you can see. It is the faint microwave glow between the stars. The background hum of creation. The afterglow of the Big Bang. It has been traveling for over 13 billion years to reach you. It is the oldest thing any human will ever observe, and you are here to receive it. On a small planet, orbiting an ordinary star, in a mid-sized galaxy, in a vast and ancient cosmos, you exist. You are conscious. You can contemplate the age and scale of the universe. You can understand that the photons of the CMB are older than any star that currently shines. You can grasp, at least intellectually, that you are surrounded by light from the very dawn of time. That is extraordinary. The universe produced matter that can think about the universe, atoms that can trace their own origins back almost to the very first moment. Beings who can stand on a pale blue dot and reach across 13.8 billion years of history to touch the edge of the beginning. The oldest moment we can ever observe is all around you. It always has been. It always will be. And the fact that you know this, that you understand what it means, that you can hold the vastness of cosmic time in your mind and feel something, wonder, awe, humility, gratitude, that is perhaps the most remarkable thing in the entire 13.8 billion year history of the cosmos. The universe is old. The CMB is ancient. The Planck epoch is beyond our reach. But you are here. And you understand. And that matters more than you might think. Thank you for joining me on this journey to the edge of time. If you found this exploration meaningful, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And remember, the oldest light in the universe is not in some distant telescope. It is here, right now, all around you. The afterglow of creation, still glowing faintly after 13.8 billion years. And you are part of the universe that can hear it. Good night. And may you never look at the sky the same way again.